All right, so good evening. I am Rania Kasadikawa, and I will be presenting the operating system for autonomous vehicles. So, for some background and context, autonomous vehicles, also known as self-driving or driverless cars, represent a significant technological advancement in modern-day transportation. Since the invention of the first automobile by Carl Benz in 1885, continuous innovation has propelled the development of automated driving systems culminating in vehicles capable of navigating without direct human control. The development of AVs aimed to reduce traffic accidents, improve mobility for individuals unable to drive, and increase overall transportation efficiency. To achieve this, AVs rely on complex real-time interactions between multiple hardware and software components. While much focus is placed on the vehicle's physical sensors and AI systems, the operating system plays an equally critical role. The OS serves as command center that these complex interactions, ensuring that data flows efficiently between sensors, decision-making algorithms, and vehicle components. The Society of Automotive Engineers categorized driving automation into five levels. From level 0, which means no automation, to level 5, which means full automation. The majority of autonomous vehicles currently under development are classified at levels 3 and 4. Level 3, meaning automation allows the vehicle to manage all aspects of driving under certain conditions, though a human driver must be prepared to take control when requested. Level 4 vehicles can operate autonomously in specific, predefined environments or conditions requiring no human intervention in those contexts. As such, this research seeks to address the problem of identifying the unique requirements for operating systems in autonomous vehicles and how these can be addressed to ensure real-time processing and safety. So this begs the question, how can operating systems in autonomous vehicles be designed to efficiently manage real-time, safety-critical and non-critical tasks, ensure fault tolerance, support secure task isolation, and enable seamless system updates without compromising reliability or performance? So this study contributes to AV safety by exploring OS designs that support real-time responsiveness and fault tolerance, which are key factors in preventing accidents and system failures. Second, it improves task management efficiency by examining how AV platforms can prioritize and handle multiple computational workloads. It also addresses the need for strong security and isolation mechanisms to protect against cyber threats and system malfunctions, emphasizing modular and scalable OS architectures that enable safe over-the-air updates. Finally, it supports regulatory compliance with the international safety standards, particularly ISO 26262, to enhance public trust in AV technology. Moving on to AUTOSAR, which is the Automotive Open System Architecture. This is a standardized software framework jointly developed by a variety of automotive manufacturers and suppliers. It is widely adopted in the automotive industry, particularly for traditional electronic control units. AUTOSAR promotes modularity and scalability by defining standardized interfaces and layered architectures, which enhance interoperability and reduce development costs. These are two primary There are two primary platforms under AUTOSAR: Classic Platform optimized for hard, real-time, low-resource ECUs, and Adaptive Platform designed for high-performance computing environments used in automated driving functions. Moving on to QNX, developed by BlackBerry, is a commercial real-time operating system designed for safety-critical applications. It is certified under safety standards such as ISO 26262 ASIL-D, making it a popular choice for advanced driver assistance systems, ADS, and other mission-critical automotive subsystems. QNX offers microkernel architecture, fault isolation, and low latency task execution, enabling high reliability and predictable performance. Lastly, we have ROS, which stands for Robot Operating System. This system provides a highly modular open source framework originally developed for robotics research. ROS offers flexibility, reusability, and extensive libraries for perception, mapping, planning, and control, making it attractive for AV prototyping and AI development. Before we head on to the research gaps, the data for this study was collected through the document analysis of academic journals in the fields of computer science, automotive engineering, and embedded systems, industry reports from companies and institutions involving in AV development, open source operating system documentation, regulatory and safety standards, and documented case studies involving real-world implementations or evaluations of AV platforms. Moving back into the research gaps, it was identified that there were six. AI integration challenges, such as current safety standards are incompatible with non-deterministic AI, requiring new validation methods. No unified OS, existing platforms such as AutoSort, QNX, and ROS, each have limitations. A comprehensive integrated solution is needed. Also regarding update safety, real-time fail-safe over-the-air update mechanisms are lacking and require further research. Scheduling limitations, traditional algorithms like RMS or EDF may not meet AV demands. Adaptive models are needed. Distributed fault tolerance, coordinated recovery across multi-core systems is underdeveloped and poses reliability risks. And lastly, testing gaps. Lack of open standardized tools hinders system validation and reproducibility. Onto the key findings, it is revealed that while current AV systems benefit from platforms like AutoSAR, QNX, and ROS, no single solution fully meets the demands of safety-critical real-time operations, AI integration, and system scalability. Real-time responsiveness and deterministic scheduling are essential for safety navigation. By integrating probabilistic AI algorithms within deterministic safety frameworks such as ISO 262 remains a significant challenge. The research underscores that AV operating systems must be designed to handle heterogeneous workloads, ensure fault tolerance, and isolate safety-critical functions from non-critical processes. Existing solutions often require hybrid integration, increasing system complexity and introducing new reliability risks. Moreover, current over-the-air update mechanisms fall short in supporting safe and uninterrupted updates, a necessity for involving AI-based systems. So for future research, practical applications include the development of safety-certified hybrid operating systems, the integration of runtime monitoring for AI components, and microservice-based OTA update strategies. Future research should focus on designing unified operating systems that combine the safety of QNX, the modularity of AutoSAR, and the flexibility of ROS, creating new safety validation frameworks for AI components that accommodate non-deterministic behavior, developing adaptive and mixed critically scheduling algorithms suited to developing adaptive and mixed criticality scheduling algorithms suited to dynamic AV workloads, exploring fault-tolerant distributed computing mechanisms for multi-core and networked AV architectures, and finally, building open source platforms and test beds for validating AV OS performance under realistic conditions. And that is all for my report on operating systems. And that is all for and that is all for my and that is all for my report on operating systems of automotive vehicles. And that is all for my report on the operating systems of autom and that is all for my report on the oper and that is all for, and that is all for my report on operating systems of autonomous. And that is all for my report on the operating systems of autonomous vehicles. Thank you.